it is really important to actually memorize those. And it's not like every day in this class is just going to be rote memorization. You know, this is not a biology class. But, you know, this packet that I gave you is kind of like the foundation that I assume we're all working on. And if you don't have that foundation, then it's going to be difficult to like have class discussions and move forward with this. And, you know, I've taught Calculus 1 a few times. And sometimes I've led with the really rigorous, fine, precise mathematical definitions of what a derivative is and how we came up with these, like kind of history of math historically, when Leibniz or Newton was sitting down at their desk and they were working these things out for the first time. How did they find out that the derivative of natural log is 1 over x, right? Like, how did people discover these for the first time? But what I found in the past when I've taught that way is that students get overwhelmed really quickly, and maybe you don't really care very much about the whole history of math bit. And so what I've tried to do more recently, and what I've had more success with, is kind of swapping the order of the course, where we really quickly try to get into application problems. I want you to start to see how the derivative could be useful when answering real-life problems that have to do with, you know, economics or engineering or whatever. And then later at the end of the semester, I promise we'll come back to a more precise mathematical definition about how we know these derivatives are what they are. But in order to kind of like jump in and get to those derivative applications as quickly as possible, that means we kind of have to just like take our medicine on the first day of class and try to memorize these as fast as possible so that we can start working. We talked about this a little bit last time, but I want to jog your memory. When we have a line in the xy plane, we can write y equals mx plus b, and this is very often called the slope-intercept formula for a line, because whenever I look at the m constant, that's going to tell me the slope of my line. And whenever I look at the b constant, that's going to determine the y-intercept of my line, where the line passes through the y-axis. And one of the things I asked you about last time, and one of the things you said, is that, well, if m is positive, that implies that the line is going to go up from left to right. In other words, we might say it's increasing. When m is a negative constant, that implies that the line is going to be going down from left to right. We might say that the line is decreasing. And if m is 0, that means it's perfectly flat. It's a perfectly horizontal line. If m is a large number, that means the slope is more steep. If m is a very small number or close to 0, that means it's closer to being flat. And so it's not very steep. And so our informal definition of the derivative, like I said, at the end of the semester, we'll give you a very formal, very precise mathematical definition. But for right now, our working definition that we're going to use informally is to say that the derivative of a function is the slope of its curve. So again, I've got an xy plane, and some curve here is going to represent y equals a function of x. And if I take the derivative of that function, that's going to tell me about the slope of the curve at every point along the curve. So now what we're going to do is I've got a bunch of examples, and for each one of these, I want you to try this. And you can do this on your smartphone too. You don't have to have a laptop. Maybe a laptop makes it easier. but even if you have a phone ready, you can go to Desmos.com, click on the graphing calculator button, plot the function just by typing in what you see, and then you can also plot its derivative. Of course, we're going to have to find the derivative first and then plot it in Desmos. And then we'll talk a little bit about why the values we see are really fit our intuitive definition that the derivative is the slope of the curve. So let me open up Desmos now. And this is my first function, y equals x squared. And it's okay if you want to look at your packet of derivative rules, but what is the first derivative rule right at the top? I think I named it like the derivative power rule, or just as power functions. I call this a power function because it is just x raised to some power. And for some power, we're using the little lowercase letter a. And we said the derivative of x to the a power is a times x raised to the power a minus 1. So somebody tell me, what would be the derivative of x squared? 2x raised to the first power. Yep. 2x, and you could say 2x raised to the first power, but x raised to the first power, you can just write as x if you want to. And so this derivative would be 2x. And I haven't actually said this out loud yet. Well, maybe I did last time, I can't remember. But if you see this notation, d over dx, the way that you want to read this out loud is you say derivative of. Okay, so I'd say the derivative of x to the a power is a times x raised to the power a minus 1. And then this little bit of notation that I wrote over here, which is dy over dx, whenever you read this out loud, you would say the derivative of y with respect to x. And sorry for the shorthand, but if I say WRT, that means with respect to. So if I say the derivative of y with respect to x, that's referring to the little dy over dx notation. So in other words, if y is equal to x squared, then the derivative of y with respect to x is 2x. And if I ever write down any kind of notation that I haven't used before, or we haven't talked about before, or if you just don't remember, please raise your hand and stop me, because it's sometimes hard to remember what I have said and what I haven't said. So I don't want anybody that can be confused. You can raise your hand and ask me. Even if my handwriting is just atrocious, you can still raise your hand and say, what are you trying to write there? Okay, so then let's plot this derivative, the 2x. Let's plot that in Desmos as well. So in red, we've got the original function. In blue, we have the derivative. And if this derivative is supposed to tell me about the slope of the red curve, does it do a good job? Well, when the red curve is completely flat at x equals 0, the derivative is 0. And where the red curve is increasing really steeply, then the derivative is a pretty large positive number. When the red curve is decreasing really steeply, the derivative is a pretty large negative number. And whenever the curve is close to x equals 0, where it's not perfectly flat, but it's relatively flat, then your derivative gives you relatively small numbers. So it does seem like the blue line is telling me about the slope of the red curve. That's what I mean on your homework when you see exercise 3 on your homework. That's kind of what I want you to go through the mental process of doing. By the way, whenever I give a lecture during class and you see like exercise numbers, that corresponds to your homework exercise numbers. So I try to at least show you a little bit how to do the problems you see on homework. All right, so the next one. What would be the derivative of this function? Three x raised to the power what? 2. And again, then I would say if y is equal to x cubed, then the derivative of y with respect to x is 3x squared. That's how I read that out loud. So let's plot that on Desmos. And let's talk about it, see if it makes sense. My original curve, x cubed, is in red. The derivative is in blue. Again, there's one part of the red curve where it's perfectly flat. So I need its derivative to be 0. Yeah, anytime your curve is perfectly flat, you expect the derivative to have a value of 0, and that works. Everywhere else on the red curve, I would say it's what? Increasing or decreasing? Increasing. Increasing means the curve goes up from left to right. And so the whole red curve is increasing, except where it's flat there at x equals 0. And so if it's increasing, is my derivative going to be positive or negative? Positive. And so sure enough, on that blue derivative curve, everything is positive, meaning it has a positive slope, except for x equals 0 when the blue curve is 0. So it makes sense. Okay. So now what if I have y equals x raised to the power 0.5? Then the derivative of y with respect to x would be
0.5x negative raised to the negative 0.5.
Mm-hmm. Perfect. I regret not making this a trickier question. I should have done this a little bit differently in my notes, because what I normally ask, what I normally have in mind is this. What if y is equal to the square root of x? And you actually do know how to do this.
It's the same as if it were raised to the 1/2. So
yeah.
That other question.
Yeah, exactly. So this is on our packet of stuff you have to memorize. This is on our handout. If you turn to the page, Properties of Exponents, the first page, and you look at number 5, there's a bunch of little lines under number 5. The third line says if I have x raised to the power 1 over n, it's equal to the nth root of x. Well, let's let n be the number 2. So if I have x raised to the power 1 divided by 2, that's the same thing as the square root of x. So square root of x is x to the 1/2 power. And so instead of thinking about the square root of x, it can be helpful to think about this as x to the 1/2 power. And then we say that the derivative of y with respect to x is
to the negative 1/2 power.
Perfect. 1/2 x to the negative 1/2 power. And another way of writing that would be to say 1/2 times, what do I do with a negative exponent? What if I don't want to have a negative exponent? One over, yeah. Perfect. So if you don't know what to do, let's look at properties of exponents number 4. Number 4 tells you how to handle negative exponents on that first page. And for a negative exponent, I can write 1 over x to the 1/2 power. And again, another way of writing x to the 1/2 power would be 1 over the square root of x. And so sometimes, because we're familiar with how square roots work, we like to write it like that. But I do want to point out that all 3 of these answers are correct. Okay? I'm not going to take off any points at all if your answer on a test is any one of these 3. Okay? If I'm writing a multiple choice test, I'm writing your answer choices A, B, C, D, E, then I might write your answer choice as this just to make it more difficult. But if it's an open-ended question and you get to write your own answer, I would give you full credit for any one of those 3. Okay? Any questions about that? No? Okay. Okay, so now let's go back to Desmos. And I'm going to type in the function y equals square root of x. And its derivative, which was 1/2 times 1 over square root of x. Let's talk about it. So the original curve, the square root of x, is in red. And there's no place where the red curve is flat. So we expect when we look at the derivative, there's no places where the derivative is equal to 0. The red curve is always increasing from left to right, so we expect the derivative to have only positive values. And the slope starts off pretty much vertical, right? And then it kind of levels off and gets more flat. So in the derivative, we expect the derivative to start off extremely large and then get closer and closer to 0 over time. So it makes sense. By the way, let me show you one way you can check your work with Desmos. And as we go through the year, you're going to realize that I have an unhealthy obsession with Desmos. But there's another type of notation we can use to designate derivatives. And this is called Lagrange notation. And the way Lagrange notation works is we say, I have a function f of x, and that's equal to square root of x. And then to denote what I'm talking about for the derivative, I write the derivative as f prime of x. So you got to be really careful and look for the little apostrophe. If it's got an apostrophe, it means I'm not talking about the original function anymore. I'm talking about the derivative of that function. And so if you see this type of thing, the derivative of y with respect to x, this is called Leibniz notation, named after the mathematician Leibniz who invented calculus. And if you see Lagrange notation, it's telling you the same thing. We're still just talking about functions and their derivatives, but it's named after a different mathematician, Lagrange, who also worked on the foundations of calculus a couple hundred years ago. And the reason I bring this up is because Desmos understands Lagrange notation. If I type this in, Do you see how the green curve gives me the derivative of that function? And I don't even have to find the derivative myself. So one way you can check your work is you can find the derivative yourself, like this, and then in Desmos, tell Desmos, hey, find the derivative for me. And then one way to check your answers on your homework is to say, is this blue curve exactly the same as the green curve when I toggle this on and off? And if it is, then you got the derivative correct. If it's not, then you made a mistake somewhere. You got to go back and find your mistake. Okay. Any questions so far? No? Is this super easy? That's good. All right. I mean, don't feel too uncomfortable to ask me questions. I really don't mind slowing down at all. If we need to slow down. So here's another question then. If my function is y equals 1 over x, then what's the derivative of y with respect to x? Another way I could ask exactly the same question is I could say, suppose my function is f of x equals 1 over x, and I could ask it like this. What is f prime of x? Same question, right? Your hint again is to look over those properties of exponents really closely. Hudson?
Negative x to the negative 2 power.
Yes. So I'm sure what Hudson is thinking is that is the same thing as x to the negative 1 power, because that's a property of exponents. And then we use that derivative power rule. And the derivative power rule says, let's take the exponent down in front, and then we reduce the exponent by 1. So negative 1 minus 1 is negative 2. Or I could write f prime of x is negative x to the negative 2 power, right? Same thing. All right. New function. This says y equals e to the x. So what is the derivative? No.
It's just e to the x.
E to the x. This is the only function that is its own derivative. By the way, do you guys know what the number e is?
Euler's number?
Yeah. Let me do another quick little aside. I got to find some blank space to write in, but the number e is an irrational number. Irrational means it's kind of like pi, and that like pi has infinitely many digits after the decimal. It doesn't ever terminate in the decimal expansion. It's like 3.14, 159, blah, 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 and it just keeps going. People have competitions to see how many digits they can memorize. but it doesn't ever stop. E is kind of like that. E is about 2.718281828, and that's the first 10 digits. I don't remember the rest of them, but it does keep going forever. You don't have to memorize those numbers. You just need to know it's about 2.7, right? It's totally fine if you just think of E as being a number that's close to 2.7. The exact definition of E, maybe you've seen it before in a different class. But if you want to know what is E really, E is the limit as n approaches infinity of this expression, which is 1 plus 1 over n raised to the n power. So what does that mean? That means if you want a good approximation of E, you could do 1 plus 1 divided by 1,000,000, all raised to the power 1,000,000. And if you want an even better approximation of E, you could do 1 plus 1 divided by 1,000,000,000, raised to the power 1,000,000,000. If you want an even better approximation, you could do 1 plus 1 over 1,000,000,000, raised to the power 1,000,000,000. And the larger the number n gets, the better your approximation of this number. But for our purposes today, we can just remember that this is about 2.7. And this is the only function, like I said, that is its own derivative. If you use any other exponential function, you get pretty much the same derivative, except with a little constant that tweaks the scale of the derivative. But if you really want the function that is its own derivative, that's what it is. And hopefully you can kind of see this. The blue curve is always increasing, so its derivative should always be positive. Very good. On the left, it's not increasing very fast, so the values of its derivative should be pretty close to 0. On the right, it's increasing pretty fast, so its derivative should be pretty large numbers. And here, the slope appears to be about 1, about a 45-degree angle, and so the value of the function is 1. I mean, everything checks out. That should be its own derivative. Okay. Y equals natural log of x. What is the derivative?
1 over x.
1 over x. Let's see if that makes sense. So the original curve is in red. Everywhere, is the red curve increasing or decreasing? Increasing. And so everywhere the red curve exists, you'll notice that the blue curve is positive. The blue curve also exists for negative numbers, negative values of x, and the red curve doesn't exist. If you want kind of a more generic definition, a more generalized definition, you could say that this function, the natural log of the absolute value of x, has the derivative 1 over x, and now you see that it makes sense for all non-zero real numbers. But in general, hopefully you can see that the red curve is never, ever, ever, ever flat, so the blue curve is never 0. And where it's increasing, the derivative is positive. Where it's decreasing, the derivative is negative. The sine function, what's the derivative? Cosine. So I'll quickly show you some of these. Same idea. You look at the red curve, the original function. Every place where the red curve is flat, the derivative should be 0. Every place where the red curve is increasing, the derivative should be positive. Every place where the red curve is decreasing, the derivative should be negative. Everything lines up perfect. Next, cosine. What's the derivative? Negative sine. So let's try that. Red curve is going to be cosine. The blue curve, the derivative, negative sine. Same idea. Original function is flat, derivative is 0. Original function is flat, derivative is 0. Original function is increasing, derivative is positive. Original function is decreasing, derivative is negative. Okay, arctangent. What is the derivative?
1 over x squared plus 1.
Okay. I always really liked this fact because arctangent's like an inverse trig function. You don't really expect the derivative to be a rational function. But we'll talk about why this is at the end of the semester too. So the original function's in red. It's never flat. So the blue curve is never 0. The steepest part of the red curve is in the middle, where x is equal to 0. That's where the red curve is most steep. So the largest value of the derivative would happen right there, where x equals 0. It's always increasing, so the derivative is always positive. All right, y'all are still doing good? Any questions? No? Okay. So now we're going to do one more exercise. I think this is the last thing we'll do today. Because sometimes we want an exact value of the derivative. And in this case, if I say my function is x to the 4th power, and I want to evaluate what is the derivative at x equals 0, the first step is going to be finding out what the derivative is in general, okay? In other words, what is f prime of x? Hold your horses just a little bit.
4x raised to the 3rd power.
There you go. Yeah, that's the answer I'm looking for first. Now, Kyle is right that now if I go look at that derivative function and I plug in x equals 0, then that's 4 times 0 to the 3rd power, and that is 0. But I just want you to work through each step before you jump to the answer, you know. I want all of the students to see where it's coming from. But that's great if you can see ahead like that. Now, next one. If my original function is x to the 5th power, what's the derivative? 5x to the 4th. And now if I look at that derivative, function, and I want to plug in -1, in other words, I want to find out what is the derivative when x equals -1, this would be 5 times -1 to the 4th power, and that would be 5. Yep. And maybe you guys all understand this, but importantly, you cannot just look at the function and plug in x equals -1, because this time g of -1 would actually be -1. Right, if I just took the function and I plug in x equals -1, that's -1 to the 5th power. Negative 1 to the 5th power is negative 1. So the value of the function, the original g function, is negative 1. But the value of the derivative of the g function is 5. Next one. If my original f function is x to the 1.5 power, then the derivative would be
1.5 x to the half.
Yeah. Now let's plug in x equal 4 to that derivative, and we get 3. Because remember, the 0.5 power is the square root. The square root of 4 is 2, and 1.5 times 2 is 3. And just for fun, what if I don't take the derivative? What if I actually just want the value of the function f, where x equals 4? Then I'm talking about 4 raised to the power 1.5. And that's the same thing as 4 raised to the power 3 divided by 2. And that's the same thing as the square root of 4 raised to the 3 power. That's the same thing as 2 raised to the 3 power. So the value of the function f at x equals 4 is 8, but the value of the derivative at x equals 4 is 3. I think it's worth graphing that one. So there's the function. There's the derivative. The function is always increasing, so the derivative is always positive. My original function, when x equals 4, has the value 8. See that coordinate pair, 4, 8? And then the derivative of that function, when x equals 4, has the value 3. And that means at that point, the slope of this curve is about 3. By the way, slope is rise over run. Did your algebra teacher tell you that? Slope is rise over run. And so on Desmos, if you zoom in really close, you can count boxes and look at this point, and then go up 1, 2, 3, and over 1. And you'll find this with all functions. Well, I should say, you're going to find this with all functions that have derivatives, is that when I'm zoomed out, this does not look like a line. I hope, right? It looks squiggly. So when you're zoomed out and you're looking at the whole function, it doesn't look very linear. But zoom in and you get really close to the function, suddenly it looks like a line. And it makes sense to talk about the slope of a curve when you're really close zoomed into it, because it's just the slope of this line, right? Even if the function as a whole is really nonlinear, when you zoom in really close, suddenly it looks linear. Here is another function that has a derivative. And again, if I zoom out, it doesn't look like a line, but if you just pick a point and you zoom in really close, well, now suddenly it looks like a line. And I can even tell by doing the rise over run thing that this is -1 over 4. The derivative here, when x is equal to 2, must be -1/4. Just doing the whole rise over run thing after I zoom in.
It'll change as you go along the line, right? Or will it stay the same as that?
No, it changes, right? Like if I pick this point and I zoom in really close, the slope is no longer negative 1/4. Now the slope is like 1, 2, 3, 4, negative 4 over a quarter. It's negative 16. The slope is negative 16 here. The derivative would be negative 16 at that point. All right, so it does change because it's not a line on the macro scale. It only looks linear if you zoom in close enough. And so I said this is true for all functions that have a derivative. And so maybe you're asking, are there any functions that don't have a derivative? This is the absolute value function. And the derivative exists everywhere, like here, right? Nice, easy derivative, positive 1. The derivative exists over here too. The derivative would be negative 1. But there is a point on this function that has no derivative. Because if I try to zoom in as close as I can to x equals 0, it never looks like a line, right? You can keep zooming, but it's never, ever going to look linear. And so we say the derivative does not exist when x is equal to 0 because there's no really meaningful way to give this a slope. It doesn't ever look linear, no matter how far I zoom in. Okay. A few more. We'll do as many as we have time for today. By the way, I should mention for this homework paper that I handed out, we talked about this last time. There is no grade for homework. You're not going to turn this into me. You're going to keep this. So I'm not going to hand you a separate test review. This is your test review. Any question that I ask you on a homework assignment could be a test question. Like it's very likely that one of your test questions is going to be like, find the derivative of 2 to the power x and then evaluate that at x equals 1.5, right? And so then you're fully prepared for the test because you've been working the homework assignment and you know how to practice that. So use these homeworks as practice, but don't feel like you have to turn it in. Yeah. Oh, you need one? Okay. Does anybody else need one? No? Yeah.
Thank you.
Mm-hmm. All right, what's the derivative of x to the negative 2 power? Very good. And again, you already know this. Sorry for wasting your time. But if I were to write 1 over x squared and ask you for the derivative, if this is a multiple choice question, I might write the answer like that. But you understand it's the same thing. 1 over x squared is the same thing as x to the negative 2 power. And then negative 2x to the negative 3 power is the same thing as negative 2 times 1 over x to the third. Okay. Okay, now if I want to actually plug in negative 1 here to find the value of my derivative at negative 1, what is negative 1 raised to the power negative 3? Yes, that's right. Because x to the negative 3 power is the same thing as this, 1 over x to the third. So negative 1 to the third power would be negative 1. 1 divided by negative 1 is negative 1. And negative 1 times negative 2 would be 2. All right, this one's a little bit tricky. What about this question where I say the function g of x is now 2 to the power x. What's the derivative g prime of x? Uh-huh.
It's the natural log of 2 times 2tx.
Very good. So this is on the page of derivatives you have to memorize, but it's natural log of 2 times 2 to the x. So now I'm going to plug in the number 10 for x is equal to 10, and that's natural log of 2 times 2 to the 10 power. You can count your powers of 2 if you want to. You can say 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024 times natural log of 2. Or, perfectly acceptable. I said on your tests, you can use a TI-30X2S calculator. Pull out your TI-30X2S calculator and just type in natural log of 2 times 2 raised to the power 10. And it tells me that's 709.8. Cool. All right, next one. Log base 3 of x. What's the derivative here?
1 over natural log 3x.
Times. Oh, it's that, right? Yeah. Okay. And so then you plug in 9. X equals 9. And that's like 1 over 9 times natural log of 3, whatever that is. Okay. Arctangent. We already said this derivative earlier today. That was 1 over x squared plus 1. And that, of course, you plug in x equals negative 2, and you get
1 over 5.
1 over 5. And so this is how you find the exact value of the slope of a curve at a given point. Right?